Welcome. On this video, we will talk about geometric sequences. So let's get started. So before we start defining geometric sequences, let's take a look at this small introduction question, which says here, let's consider the sequence, which notice that this is an explicit formula. And let's start by finding the first five terms of the sequence. Well, since this sequence is explicit, then all we gotta do is just plug in values of n so we can obtain our terms. So if we let n equals to 1, then we're going to have the value of the first term. So if we plug that in, if we let n equals to 1, we're going to have 1 over 2, 1 minus 1, because all we did, we substitute the value of n to be equals to 1. So now this is 2 to the first to the 0, 1 times 1, which is just 1. So now to find the second term, again, all we got to do is we're going to go to our explicit formula and we're going to substitute n to be of a value of 2. So now we're going to have 1, 2, 2 minus 1, 1 of 2, 1. So now that is 2. And I'm just going to save some computation and I'm just going to write down the results. So this is my second term. My third term, if we would have plugged n to be equals to 3, we would have got a value of 4. To get the fourth term, we would have let n equals to 4. And if we would have plugged in 4 to our equation here, we would have got 8. And lastly, if we would have plugged in n to be equals to 5, then our result would have been 16. Okay, so here we have our first 5 terms. So first term, second, third, fourth, and fifth. So we have found on the first 5 terms. Now, there seems to be a pattern between the terms of the sequence. Well, let's write them out here. So my first term is 1, my second term is 2, my third term is 4, my third term is 8, my third term is 16, and there's more. Now, if we just write them out, and if we take a look at just the value of the terms of the sequence, there seems to be a pattern between how do we get to the next term. But notice that there's a simple pattern here, because if we multiply the previous term times 2, we get the next one. 1 times 2 is 2. And if we multiply that times 2, well, that's 4. And 4, if we multiply it times 2, well, that's 8. And 8, if we multiply it by 2, so that's 16. So notice that there seems to be a pattern between the values of the terms in the sequence. And that pattern is that to get to the next term, it seems like all we did, we just multiply by a value of 2. So that seems to be the pattern that we got by just taking a look at the values of the terms in this sequence. Now, let's try to see what happens if we decide to plot the values, or at least the values of the terms in our sequence. So let's graph the points in the sequence. Now, recall that whenever we want to plot, at least in the terms of sequence, our x-axis is going to be the term number, and our y-axis is the actual value of the term. So let me create a table of values and I'll be back in a second. Okay, so we're back. So here, all I have done, I have just created a table value with the results that we got in here. My first term has a value of 1, so I'm going to have 1 comma 1. So let's do that here. So we have our first point here, 1 comma 1. My second term had a value of 2, so therefore I have a point at 2 comma 2. So 2 comma 2 right here. My third term had a value of 4, so I'm going to have a point at 3 comma 4. So 3 comma 4. My fourth term had a value of 8, so I have a point at 4 comma 8. So 4 comma 8, so about right here. And my next point, or I'm sorry, my next term, which is the fifth term, had a value of 16, so I'm going to have a point at 5 comma 16. 5 comma, I'm going to say 16 is somewhere around here. So now, if we were to plot this, notice that we're going to have the shape of a very particular function. Because if we were to plot this, if we were to connect those points, Okay? If we were to connect those points, I mean, we know that this is going to increase infinitely. But what kind of a function do we seem to have here? But notice that we seem to have an exponential function. We seem to end up with an exponential function. And all we have done now is we have properly actually analyzed what an exponential, I'm sorry, we have properly analyzed what is a geometric sequence. A geometric sequence is what we have just done here. A geometric sequence is a sequence who has a pattern of either multiplication or division, whichever. And if we were to plot the value of those points in, if we let our x-axis be the term number, and we let our y-axis be our value, if we were to plot them, they will always behave as an exponential function. So this is actually what a geometric sequence is. It is a sequence which has a pattern of either multiplication or division, and if we were to plot their values, their function, it will behave like an exponential. And notice that this behavior of this function, it actually goes hand in hand with the exponential, with the sequence, with the explicit equation that we have for our sequence. Notice that our sequence, it's an exponential equation. Here, notice that the only variable, it's on the exponent. So therefore, if I were to plot those points, it should behave like an exponential. So this is what a geometric sequence is and how it behaves. But now let's just jot down an actual explicit. Well, let's actually define the geometric sequence properly. So here we're just going to talk about here's just a regular sequence. We have first, second, third, fourth, fifth terms, and then just infinite sequences. So how are we going to define a geometric sequence? So a geometric sequence is a sequence where the next term is calculated. Let's use the word calculated. Where the next term is calculated by multiplying or either by divide by a constant number. So if your sequences have the same pattern, and that pattern is either a multiplication or division by the same number, then we can call that kind of a sequence a geometric sequence. Now, the common ratio, it's the constant number, or is a constant value or number, which we multiply again, it could also be division, to obtain the term in the sequence, to obtain the next term. In the sequence. Which in this case, if we take a look at the example that we just had previously here on our introduction question, in this case, our common ratio will be a value of 2. And again, we don't call it a common ratio of times 2. The common ratio is just the actual value. The actual value. Now, is there a way for us to properly calculate the value of this common ratio? Yeah, because to calculate the value, all we got to do is get one term and divide it by the previous one, or an over an minus 1. What I'm trying to say here is that choose a term in the sequence. If you divide it by the term that came before it, it should give you the value of the common ratio. Take a look. 16 divided by 8, well, that's 2. 8 divided by 4, well, that's 2. 4 divided by 2, well, that's 2. 2 divided by 1, so that's 2. So that's what I'm trying to say here. To calculate the value of the common ratio, all you got to do is just get a term and just divide it by the previous one. Now, is there a way that we can write down an explicit formula for a geometric sequence? Well, we know how geometric sequences behave. All it does is, in order for you to get to the next term, you got to multiply by this so-called common ratio. So let's see if we can identify a explicit formula that we can use for all geometric sequences. So for me to get the first term, well, that's the first term. Now, for me to get the second term, which in this case, consider it to be 2, all we did, we got the first term and we multiply by the common ratio. And for common ratio, we're going to use the letter R. Now, to get to the third term, so here we have our first term, here we have our second term, and all we have said is to get to the second term, all we got to do is multiply by this so-called ratio. Now, to get to the third term, notice that we got to multiply by another common ratio. So to get to the third term, we can say, well, that's the second term times a ratio, or we could say that is the first term times 1, 2 ratios. So we're going to have the first term times a ratio, which this is just equivalent to the first term times the ratio squared. Now, how will we get to the next term? Well, to get to the next term, again, all we can do is get the third term and multiply by another ratio. Or we could say that is one term, it is the first term, times 1, 2, 3 of those ratios. Which this is equivalent to the first term times r to the third. And let's just do one more. So to get to the fifth term, all we got to do is get the fourth term and multiply by this common ratio. So we can say that the fifth term can be defined as the fourth term times a ratio, or we could say that is the first term times 1, 2, 3, 4 of those ratios. Which this is equivalent to just the first term times the ratio squared. And at this point, we can start seeing a small relationship between the values that we get in here. Because notice that we're always going to have the first term times some ratio. That's something that it doesn't really matter which term we're looking for. They all have to be starting by the first term. So that's something that they all have in common. And they all have to be multiplied by some kind of a ratio. But now the only thing that keeps changing is the value of the exponent of r. Right now, you can see that the exponent is 1. But now notice that in order for me to find the fifth term, r was raised to the fourth. For me to find the fourth term, r was raised to the third. To find the third term, r was raised to the second. So notice that the value of the exponent, it's always going to be 1 less than the term that we want to define. And thanks to this small relationship, then now we can define the explicit formula for any geometric sequence. So for any geometric sequence, we can say that any term, it is equivalent to the first term times r, and the value of the exponent, it's always going to be 1 less than the term. So if the term right now is n, then right now my exponent should be n minus 1. And this is how we're going to be defining geometric sequences, where again, an is the term that we're looking for, a1 is the first term, r is the common ratio. So if we know that we have a geometric sequence, then we can use this explicit formula to define its term. And notice what we actually need to define this geometric sequence. all we need to define a geometric sequence is just the first term and the common ratio. So let's do some examples using our discovery now. Let's find a formula for the n term of the following sequences. And once we have done that, let's find the 9th term of the sequence. And again, for me to define an explicit equation, which is exactly what we're asking here, find the formula for the n term of the sequence, it's just saying define a geometric sequence. All we got to do is define the first term, which in this case we know it's 5. And all we got to do is find the common ratio. So how can we find the common ratio? Well, the common ratio, we can always get one term and divide it by the previous one, which in this case, that's going to be 3. So now that we have the first term and we have the common ratio, now we can say, well, the explicit formula, I know that it looks like this, an equals a1 times r n minus 1. Let's just plug in what we know. Then, at least for this example, it's going to have the form of 5, which is my first term, times r, oops, sorry, we don't put an r there because we actually know the value of it, which in this case is going to be 3 n minus 1. Now, please don't make this mistake. This doesn't mean that this is an 15 n minus 1. 5 has an exponent of 1, so we cannot just combine them. If this would have, no, this is just different. 5 is just by itself. 3 is the one that has an exponent of n minus 1, so therefore we cannot just combine them and just call it 15 n minus 1. So now that we have this, we have an equation that we can use to define any term in the sequence. So now that we have this explicit formula, let's find the 9th term in the sequence. So to define the 9th term, all we got to do is go to the equation that we have just defined, and let's just let n have a value of 9. So let's just do that. So now we're going to find the 9th term is equals to 5 times 3, 9 minus 1, which in this case, it's a to the 9 equals 5 times 3 to the 8. And if we would have done this in a graphing calculator, we would have gotten the result of 32,805. So notice how things become a little more easier if we have an explicit formula. Because another way that we could have done this is we could keep multiplying by 3. So 5 times 3 is 15. Times 3, it is 45. And if we would keep multiplying times 3 until we get to the 9th term, we would have gotten the value of 32,805. Now let's take a look at something a little more, not as straightforward as example 1. So let's take a look at example 2 now. So it states the 4th term of a geometric sequence is 125, and the 10th term is 125 or 64. Let's find the 14th term. So I guess one way that we can do this is let's actually draw what's going on here. So we can say, well, I know that there's going to be some kind of a sequence going on here. And I know that my first term, second, third, fourth, fifth, sixth, 7, 8. I guess we're missing some. So the 9th term, 10, 11, and we're gonna go all the way to 14. Let me just erase this. So here we can place the 12. Here we can place the 13. Here we can place the 14. Okay, so we got a sequence, and I'm just putting placeholders. So let's see what we have here. So it says the 4th term of the sequence is 125. So on the 4 space, we're gonna put 125. Okay, so and the 10th term of the sequence It's 125 over 64. So here we have the 10th term, and let's place the value there. And our objective is to find the 14th term on the sequence. Now, let's try to understand what's going on here. There's a lot of terms that are missing here. There's a lot of terms that we're missing here. But notice, since we know that this is a geometric sequence, I know that in order for me to go from one term to the next one, I should have multiplied by some value, which is the common ratio. But now, since we only know the value of the fourth term and the third term, let's figure out how many r's we needed to multiply to go from the fourth term to the 10th term. So we would multiply 1r, we multiply by 2r, by 3r, by 4r, by 6r, and by 7r. I'm sorry, there's 6r. So now we have a small equation here which we can use to define the value of r. Because now we have a small equation here which states the value of 125 over 64, that was equivalent to 125 times 1, 2, 3, 4, 5, 6 r to the 6th. And now doing this, we can definitely find the value of r now. So let's solve for r. So to solve for r, we're going to start by multiplying 1 over 125, both sides. And that way, notice that this is going to cancel out with this, and it just so happens that this is going to cancel out with this. So now our result is that we have 1 over 64 is equal to r to the 6th. And at this point, we want to isolate the r. And to properly isolate the r, we got to take the 6th root. So now this is going to cancel out. So now we have that r has a value of the 6th root of 1 over 64, which again, this is equivalent to the 6th root of 1 over the 6th root of 64, and the 6th root is 1, and the 6th root is 64. This is just 2. So now notice that we have that r has a value of 1/2. And we're good, because if we want to find an explicit equation, we need the value of r, and in addition, we need the first term. So I know that if I go forward, that would have happened if I would have multiplied by 1/2. So I know that in order for me to go forward, I needed to multiply by 1/2. So if I would have keep multiplying by 1/2, that's how I reached to here. So now if I want to go backwards, instead of multiplying by 1/2, I could have divided by 1/2, which is essentially just saying multiplying by 2. So now we can create another equation to properly define the value of the first term, because now I can say that the first term is equivalent to 125 times 1, 2, 3 of those r. So r to the 3rd. So it's not r to the 3rd, but here we know that we're actually multiplying by 2. So this will be 2 to the 3rd. And at this point, this is just a matter of actually finding that value. So the first term, if we put this on our graphing calculator, this is going to give us a value of 1,000. And now notice that we have everything that we need now. Because now for this geometric sequence, I know that this is a geometric sequence, which the first term is 1,000. And it also has a common ratio of 1/2. So therefore, its explicit formula will have the value of 1,000 times 1/2 and minus 1. And once we have this equation now, then we can find any term that we want in the sequence. And again, our example here, it says we want to find the 14th term in the sequence. So all we got to do is coming up with our equation. The 14th term, we're going to let n equals be 14. So let's do that now. We're going to get a to the 14 is equal to 1000 times 1/2 of 14 minus 1. Because again, all we did, we substituted the value of n to be equivalent of 14. So now this becomes a to the 14 is 1000 times 1/2 raised to the 13. And if we do this on our graphing calculator, we would have gotten a result of just 125 over 1024. So if we go back to our equation here, perhaps right here on the 14 slot, we could write down the expression 125 over 1024. And this is actually what we wanted to. And I mean, another way that we could have done this is we could have got a 125 over 64 and multiplied by an r 1, 2, 3, 4 times, and we would have got the same result. But it's preferable for you to define the explicit formula for this geometric sequence, and then you can just apply to find any term in the sequence that you want to. So this concludes our lesson for geometric sequences.